the end of the story, we must be ready to consider a vector space V and an inner product in general. Okay? And we must define the properties in common in the set of inner products. So exactly as we have seen that the concept of arrows allows us to generalize the structure, and we defined the concept of vector space, and we have found many vector spaces having different properties, but all in common have the properties of a vector space. So, as we said, the concept of vector space is as general as the concept of human being, and the set of arrows of displacement is an example of vector space, exactly as Erden is an example of human beings. In this way, we must also accept that given a vector space VB, we may have a generic inner product defined in it, and only one specific inner product is the Euclidean inner product. Okay? So, how do we define an inner product? We already said it, but we repeat it. An inner product is a particular tensor, because the inner product is a bilinear map defined in VB, Cartesian VB, having values in R. So I hope that now you are as excited as I was when, being a student, I understood this thing. The general theory of tensor algebra allows us to regard the concept of inner product as a particular tensor. It is a 2 times covariant tensor. Why? Let us check. We can use easily the tensoriality criterion if you like. You have L A B V A V B equal alpha, and alpha is independent of the basis, because the inner product V, sorry, here is W, VW, our inner product, being a bilinear symmetric So we also have that LAB is equal to LBA. This is symmetry. You can represent the inner product in this way, and as alpha by definition is independent of the basis, when you write the components VA and WB of V and B in your basis, you get this formula, and these are the components of a tensor, and they are respecting the rules of transformation when you are transforming the basis. Okay. Usually, we help ourselves. Okay, even if it is dangerous. Okay, I must learn that even if it's not completely correct in English in this context. So, albeit it is dangerous, sometimes it is useful to introduce a matrix for LAB. Now, why it is dangerous? For many reasons, including the fact that I don't know if I prefer to use A or B as a row or column index. Okay. But the ambiguity about rows and columns is not dangerous here, because L is symmetric. So we will not get any terrible effects if we don't specify which are the rows and which are the columns in the matrix representation in an inner product. Okay? Okay. Now, we require that V equals 0 if and only if V is 0. This is non-singularity of inner product. Okay? Now, let us write this. Okay, I think that maybe I want to repeat another time. I want to repeat another time the calculation. So V A E A comma V B E B equal V A E A comma V B E B, linearity with respect to the first vector argument of the inner product. It is also equal to VA VB EA comma EB. And what is this? This is the inner product of EA with EB. Okay. So what we have called here LAB is nothing else than the inner product of the vector EA in the basis with the vector EB in the basis. Okay. So if EA is orthonormal, then LAB is equal to delta AB. Delta is the Kronecker delta. Delta AA is equal to 1, and delta AB is 0 when A is different from B. Okay. So we moved another step towards understanding how the generic inner product is built. Okay, now let us go back to non-singularity here. So I know that L, A, B, V, A, V, B is equal to 0. Okay. Okay. This must imply that the determinant of LAB as a matrix is different from 0. Okay. So how do we prove this? Okay, I hope that you are not, if I want to prove that a statement implies another property, I hope that, okay, this is not complete what I'm telling you. So let us write it in very precisely. Then, when logics is in, we want to prove that this implies VA equals 0. Okay. The other implication is trivial. Okay. And we want to prove that this equivalence implies that determinant of LAB is different from 0. So this is proposition A, and this is proposition B. I hope that you are familiar with the basics of logics. So I have that the property A implies the property B. Okay. Now I hope that you know that this is equivalent to negation of B implies negation of A. So I want to prove that when A is true, then B must be true. Okay. And I tell you that this is equivalent to say that when B is false, A must be false. Tertium non-dator. This is the Latin expression we learned by heart, because you don't have any other possibility. A either is true or it is false. So let us slowly say this in detail, because I'm afraid that you didn't study these things in detail enough. Okay, so imagine that A implies B, you know. Okay, and then you know that non-B is true. Okay, if non-B is true, then B is false. If B is false, A cannot be true, because if A were true, B could be had to be true. So we can conclude that A is false. Okay. So non-A is true. And this is this implication. But you know, this equivalence is based on the fact that a statement either is true or it is false. Okay? And not every statement which we pronounce is formally correct in this way. If I tell you tomorrow it will rain or it will not rain, this statement is always true. So this is useless. But I can also tell you something which is neither true nor false, or every twisted combination of these things. In our case, we have two mathematical statements which are totally well posed. So I will prove this implication in the other way around. Determinant of LAB equals 0 implies there exists a V different from 0 such that LAB VA VB equal 0. Okay, and this is trivial using Brusche-Capelli theorem, because what I do, I write LAB as a matrix. Okay, as I know that this matrix of coefficients has determinant equal to 0, it has an element of the kernel different from 0, such that this is equal to 0. I know that the kernel of LAB is different from the singleton of 0, of the vector 0. You know, the solution of this homogeneous linear equation is made by the only vector 0 if the matrix LAB has determinant different from 0. When the determinant of LAB is equal to 0, then this homogeneous equation here has non-vanishing solutions. So the kernel is different from the singleton of the vector 0. Okay? So to say it simply, I have a non-vanishing vector, which is solution of the homogeneous equation. Obviously, L, A, B, V bar V, V bar A is equal to 0, because 0 times everything is always 0, and you sum 0 times V bar 1, 0 times V bar 2, and so on. So we have proven that there exists a V such that this is equal to 0. The inner product of V times V is. So even if I did it very complicated, I think that I was very precise and I told you everything in detail. So if you have troubles with this reasoning, please repeat it until you understand everything, because we will do this kind of reasonings many times. By the way, I have learned this in high school. And okay, simply for resting a little bit before we proceed, I have found a book, 1906. This was the book of logics of my grandfather, who studied in high school for becoming a lawyer. Okay? And, you know, this is called contra-nominal. The fact that A implies B is equivalent to non-B implies non-A. So the contra-nominal is equivalent to the so-called direct implication. This is not higher mathematics. Since the beginning of 20th century, even lawyers accepted the idea that this kind of reasoning must be understood by all of them. So I think that you will not try to claim that engineers must know less logics than lawyers. Okay. I think that in this way you can get this theorem proven very quickly, while if you try to prove it in the direct implication, you could have some troubles. Okay. Okay. So we nearly ended this lecture. We are ready to define the one-to-one correspondence between VB and V star B that is independent of the basis. You know, look, mathematics is wonderful. This is, I tell you that also my father is a lawyer. I was the first in the family who decided to study something else. But when I was a child, my father taught me that the beauty of mathematics is the following. Mathematics is a sequence of very, very simple statements, but many simple statements built one on the top of the other. So we spoke about a vector space, one specific, the set of displacements. Okay, and we studied it. Then we generalized, and we spoke about a generic vector space. Then we built tensor algebra on it. Then we recognize that the inner product is a particular two covariant tensor. And what we do, we recognize that the Euclidean inner product, I call the Euclidean inner product the one for which VW is equal to the length of V, length of W, cosine of the angle between them. And this you measure with the ruler, and this you measure with the goniometer. Okay? So this is a very specific, if you like, practical inner product. This is the inner product used by practical topographers. Okay? You recognize that the inner product is a particular two covariant tensor and that the Euclidean inner product is a particular inner product. Okay? And now you have VB and your inner product. And what you do? You associate to every V in VB, you associate LV, which applied W is equal to V inner product W. So when this is fixed and this is variable, this gives you a linear map with respect to the variable W. Okay, now we are late. We will prove in the next lecture, next Monday, that the map associated to VLV is 1 to 1. Clearly, I don't need to prove, it is evident, it is independent of the basis. So we can conclude that adding structure to VB, we managed to invent an identification between vectors and covectors that is independent of the basis. Every physical theory needs an inner product. Otherwise, you cannot build in an appropriate way the tensorial algebra on it. Okay. So in a sense, without inner product is an essential tool for developing physical theories. Okay, so I think we can stop now. Look, I am